Hello everyone, welcome to Gate Forum. So in this video, I will discuss support and support reaction. That means today from this video, we are starting shear force diagram and bending moment diagram. So today we are starting. So we will continue this shear force bending diagram for the rest remaining 3-4 lectures, means next 3-4 lectures. And as you can see, I am providing you a series of videos for strength of material on this Gate Forum YouTube channel. You can watch all the videos of this series. All the videos are very crisp and very interesting, to the point only, for gate examination point of view, whether you're from mechanical engineering as well as you're from civil engineering. Okay, so let's enjoy this topic. Here, introduction. First of all, what do we mean by beam? If we discuss about beam means any member which is subjected to lateral load. That means, suppose if you are saying that this one is a beam here, na? So beam means subjected to lateral load like this. Here we have load, here we have load, here we have load, here we have load, like this only. That means you can see what is the meaning of lateral load. Suppose if here we have a cylinder, if the cylinder will be acting as a beam, so this will be axis or axial direction. This will be axis or axial direction, I can say axial direction. Axial direction here we have, or axis here we have. But what about direction which is perpendicular to this axial? Means if here we have 90 degree, if here we have 90, this one is known as transverse direction. This one is transverse direction. And if load is applied in this transverse direction, that means definitely load will be transverse load. If load will be acting here like this, this load will be known as transverse load. And if there will be transverse loads on any member, that member will be acting as a beam. So this is a beam here we have. And what about column? Since this is not a column chapter, even though I'm telling to you, what about column? Because during the construction of house, you used to say proper beam and proper column should be there for a good structure. Okay. So what I can say, what is column? Same cylinder can be used. As column also. That is not a problem. Suppose I am using the same cylinder as a column. Only. Same cylinder, not the different one, which can be used as column also. But here, axial load should be here. If this one is subjected to axial compressive load, then this will become a column. Here. Please remember, the same rod or the same bar or the same cylinder can be treated as beam also, can be treated as column also, depending on the type of loading. If loading is transverse loading or transverse load here we have, if here we have transverse loading or transverse loads here we have, then that is known as beam. In that situation, that cylinder will be known as beam. But if the same cylinder subjected to axial compressive load, in that condition, the same cylinder will be known as column. Same cylinder can be called as beam. Same cylinder can be called as column, depending on the type of loading on that cylinder. Understood, I think. Transverse load as well as axial compressive load for beam as well as column. First of all, introduction of beam done here we have, and why we are designing the beam, so that it can carry transverse load and it should not fail during carrying the transverse load. Okay, now we are going for the types of supports. How many types of support? Then we will go for how many types of load, and then we will go for different types of beam, and then we will go for the calculation of the support reaction, which is very important in the chapter shear force bending moment diagram. Because in the PYQ, in the previous year gate question, what I can say, so many questions asked, find the support reaction. And support reaction, if not asked support reaction, even though we need to calculate, because whenever maximum bending moment, whenever shear force, we need to calculate, definitely the first step is to find support reaction. Okay, so type of supports and type of support reactions we will discuss here. So very simple. How many types of support? So we have types of support. First type of support here we have, which is known as roller support or roller support here, or somebody saying simple support also. roller support. Here we have roller support. What is the meaning of roller support here? Represented like this. Suppose here we have a beam and this one is the support which is known as roller support. If we have roller support, if we remove the roller, instead of roller we have one. Instead of we have one support reaction only perpendicular to this. Perpendicular to this, here we have support reaction roller support. What about hinge support? Second one is the hinge support here. And once again, I am telling to you, this is not a full course. This is not a full course where I am dealing all the things in very detail. Here, this video series I am providing on YouTube channel free of cost to all of you so that you can prepare a GATE exam by yourself. You can get some idea only, some important points only, and definitely by watching these videos, definitely you will solve so many problems also. But something left, 1%, 2%, very important points left. Whatever things left, we will be discussing in full course or paid course of GATE Forum, which may be not of one half hour, 1 hour. Means full course will be of 50 hours, 60 hours, more than that only. So definitely, if you want a full course, definitely join us. Join GATE Forum. Okay. So here for hinge support, if I am talking about hinge support, it will be like this here. It will be like this, represented like this. It will be represented like this here. And roller will be like this also. One more diagram for the roller. Let me draw. In the books, roller will be represented by this. Roller will be represented like this. And here we have hinge support. In hinge support, what I can say, here we have two support reactions. One is Rx, another one is Ry. Here we have Rx and here we have Ry. That means in the roller support, here we have one unknown. Here we have one unknown, but here we have two unknowns. But here we have two unknowns in the condition of hinge. But third one is the built-in or cantilever. Third one is the cantilever or which is also known as built-in support. Here we have one unknown, here we have two unknowns, here we have two unknowns, and here we have three unknowns. Here we have three unknowns, two unknown and one unknown. Here we have this one. Roller, hinge support as well as cantilever or built-in support here. Okay, now we have types of support first of all. We have done three types of support only we are going to discuss first of all. Okay, now we will go for the types of beam. Types of beam, not types of support, but we are going for the types of beam only here we have. So in the types of beam, I'm just writing this. I'm writing types of beam. Types of beam means suppose here we have a beam and supported at 2 point. One is the hinge, another one is a roller. So this is known as simply supported beam. This one is known as simply supported beam. Here we have this one is known as cantilever. Here we have this one is known as cantilever beam. Cantilever beam here we have. Okay, this one is known as, suppose here we have like this. Suppose here we have hinge and roller, three or more than three roller like this. Then what I can say, this is known as continuous beam. Simply supported beam, cantilever beam, and this one is known as continuous beam. Continuous beam because three or more than three supports are here we have. This type of beam is known as overhanging beam. This type of beam is known as overhanging beam. Here we have hinge and roller, some part on the left hand side or some part on the right hand side or some part on both the sides hanging without the support. This is known as overhanging beam. Overhanging beam here we have. Okay, this type of beam is known as fixed beam here. If it is cantilever on both the side, this one is known as fixed beam. This one is known as fixed beam here we have. Okay, this one is known as propped cantilever beam. If here it is a cantilever, but one roller here at the free end, this is known as propped cantilever beam. Propped cantilever beam here we have. So as you can see here, mostly in our examination, this beam, and this beam used to come. Very rare this beam, that is fixed beam. So do not go for the fixed beam. I'm telling to you, just go for simply supported beam, cantilever beam, continuous beam, overhanging beam, as well as propped cantilever beam here we have. Okay. Now we will go for the types of beam we have done, and now we will go for the types of load with respect to the area. Types of load, just look at here with respect to the area here. So if you are going for the types of load, Types of load here we have. So first one is known as point load or concentrated load. Point load, or which is also known as concentrated. Point load or concentrated load. So what happened here in case of point load or concentrated load? Suppose here we have a beam, let's say simply supported beam. Let's say simply supported beam here we have, and one this load W is acting. So this is known as point load. Load acting at one point only. This is known as point load. Second one is the distributed load. Second one is the distributed load here we have. Second one is the distributed load here we have. So in case of distributed load, what I can say, uh, it can be UDL, uniformly distributed load. It can be UVL, uniformly varying load. It can be UDM, uniformly distributed moment, like this only. It can be like this. Suppose first we are going for, suppose first we are going for UDL. Suppose we are going for UDL means uniformly distributed load. Distributed load, but uniformly distributed load. Uniformly distributed load. Load is not distributed, means some value of load distributed here, some there, not like that. Not uneven, but load is even, or uniform distribution of load. At every point concentration of load will be same on the beam. Okay, suppose here we are showing uniform UDL like this. Here we have a suppose simply supported beam. Simply supported beam here we have, and here load is acting like this. Here on this beam load will be acting. Load will be acting like this. Just look at here. It can be represented in two different ways. It can be represented in the two different ways. Okay, like this. I'm telling to you. As you can see here, either you can represent like this, okay, writing W Newton per meter, or you can represent like this, W Newton per meter. Both are same. Both are same. Different way of representation. In books, it is represented like this in books. In our class notes, we are writing like this. We are writing like this only. So both are UDL, uniformly distributed load, UDL here we have. Now what happens in case of UDL? What I can say, any type of distributed load can be converted to point load. Any type of distributed load, I'm writing any type of distributed load. Any type of distributed load can be converted to can be converted to point load. Can be converted to point load. Any type of distributed load can be converted to point load, but how? We are discussing on the next page. Okay, any type of distributed load, whether it is UDL, whether it is UVL, UDM, it can be acted at one point only. It can be converted to one single point load. How it can be done? Just look at here. How it can be done? We are writing here. How it can be done? Just look at here. How it can be done? Just look at here. Suppose here we have UDL. Suppose here we have UDL. First of all, here we have beam. First of all, here we have beam. Let's say here we have hinge and here we have roller, and one point load, one UDL is acting here. One UDL is acting here. Let's say UDL is here. UDL is acting here like this. This is also known as rectangular load here. This is also known as UDL or rectangular load. This is known as UDL, unit load, or it is also known as rectangular load diagram. Rectangular load diagram. Rectangular load diagram, I can say. Rectangular load diagram, I can say here. Why it is rectangle? Because as you can see, the black color is the load in terms of W Newton per meter, and this red color is the beam. Red color is the beam and support here. So what happened here? What is W? W is this length is the W. This magnitude is the W. Here we have W, and this is the length of the beam L. This is the length of the beam L here we have. Now what happened? if we want to convert this UDL into a point load, so what I can say, point load, equivalent point load will be equivalent point load will be equivalent point load will be equal to the area of the load diagram. Area of load diagram. Area of the load diagram here I can write. Area of the load diagram here I can write. How is the load diagram? Rectangular load diagram here we have. And what is the area of rectangle? Length into width. Length into width. So the point load, equivalent point load P will be equal to length into width. So here we have W into L. W into L is the value of equivalent point load here in terms of Newton. In terms of Newton, I can say W into L, and this point load will act at centroid of load diagram. This point load, this point load will act. This point load will act at centroid of load diagram. Please remember, at centroid of load diagram. Centroid of load diagram here I can say. Centroid of load diagram. That means here, how is this rectangle and where is the centroid of rectangle? Suppose here we have rectangle. Suppose here we have rectangle. Where is the centroid? Somewhere here. Somewhere here. That means if we go for lengthwise, here it is L by 2, here it is L by 2, here it is L by 2, here it is also L by 2. That means point load will be acting somewhere here. Point load will be P, which is equal to W into L, will be acting like this only. So here you can say, suppose here we have beam, then you can say, sir, this is the load, this is the beam, this was the beam, and here we have one hinge, sir, here we have one roller. So where at the center point, sir, at the center point, this equivalent point load W into L will be acting in terms of Newton at a distance of L by 2, sir. Here also L by 2, here also L by 2, like this only. So this can be converted to this. This can be converted. This can be converted to this. That means this distributed load UDL can be converted to a single point load W into L. So please remember, equivalent point load will be always equal to the area of the load diagram first of all, and that point load will be acting at the centroid of the load diagram. So please remember, area will be the value of the point load and it will act at the centroid of the load diagram. Please remember, very simple. Very simple. Okay, similarly, I can go for UVL also. Similarly, I can go for UVL also. Just look at here. Similarly, for any type of distributed load, this will be valid for any distributed. Suppose I am going for the UVL. That means uniformly varying load. That means uniformly varying load. If I am going for uniformly varying load, if I am going for. So what I can write for this uniformly varying load here? Suppose beam is here like this. Suppose here we have beam and some hinge and roller supports here we have. Hinge and roller support here we have. Suppose I am writing the writing the load here. Load is not U, it is UVL right now like this. Here it is right now UVL, uniformly varying load. Uniformly varying load like this. Uniformly varying load W Newton per meter. Here what is W? W is again the highest magnitude. W is again the highest magnitude W here, and L is the length of the beam. And L is the length of the beam from here to here. So what about P? What about P? Equivalent point load. So which is equal to area of the load diagram. Area. What about area? Area of triangle. This is triangular load diagram. Now. This is a triangular. Previous was rectangular. Triangular load diagram. Triangular load diagram. Here we have. Triangular load diagram. Here we have. Here we have triangular load diagram. So triangle half into base into height. Half into base, which is L into W. So what is the equivalent point load? Equivalent point load will be WL by 2 first of all. Equivalent point load will be WL by 2. And where it will act? It will act at the centroid. So for triangle it is 1/3 here. So for triangle it is somewhere here. Somewhere here it is 1/3 here. So you can write in this way, sir, that here we have beam, sir. So here we have beam and hinge and roller supports are here. Here we have hinge. Here we have roller supports. Out of length L, it will be acting here, sir. 1/3 and 2/3. So here equivalent point load WL by 2 will be acting here point load at a distance of how much? At a distance how much? This will be L by 3. L by 3 and this will be 2L by 3. 2/3 of L, 1/3 of L. So this will be 2L by 3 and here we have L by 3. So this point load will be acting here. So this will be converted to this. This will be converted. So I think you understood. I think you understood that how we can convert UDL or UVL to any point load. UDL or UVL to any point load. Definitely I can say you have learned. Area and centroid of area. Area is the magnitude of the equivalent point load and it will act at the centroid of the load diagram. That's it only, nothing else. Nothing else only. Very simple. Nothing else. Very simple. Okay. Now we'll move to the support reactions. Now we'll move to the support reactions. Okay. Here we have support reactions. Moving to the support reaction. Moving to the support reaction, how we can calculate support reactions. So first I will go for step by step support reaction and then I will tell you the shortcut. Then I will tell you the shortcuts. Here, suppose I'm writing like this, that here we have one hinge and roller support. Hinge and roller support, that is simply supported beam, and one point load is acting here W at the center, which is at L by 2 length, which is at L by 2 length here. So how we can write RA and RB support reaction? This is point A and here this is point B here. So find out RA, what is the support reaction RA and what is the support reaction RB. So very simple, you can say, sir, just remove the support, you will get a support reaction here RA here. You will get support reaction RA. Then you can say, sir, this is the hinge point. Na? So for hinge, you have told two support reaction, RX, RY. So since there is no load acting in this direction, so remove RX only because it will be 0 only. And here we have RB due to the roller. Here we have RB and here we have point load acting here. Here we have point load acting here like this only. So here this point is A and this point is the B and the load is acting at this point C. Load is acting this point C. So first what I should study, summation of moment at any point, let's say point A equal to 0. If I'm writing this equation, summation of moment at any point equal to 0, then what I can write from here? What I can write from here, just look at here. I can write about point A na. So I can write W multiplied by L by 2. W multiplied by L by 2, which is clockwise positive I'm taking. You can go for negative also, that is not a problem because this is not a sign convention. This is only calculation. Okay. And then minus RB multiplied by L is equal to 0. So after solving this equation, I will come to know what is the value of RB. So the value of RB support reaction here we have, which is equal to W by 2, which is equal to W by 2 here RB. And now we will be using, since we know for equilibrium, summation of force in y direction equal to 0. Summation of force in y direction 0. Total upward force equal to total downward force. So you can say that RA plus RB, which is equal to W. Total upward force equal to total downward force. You can put the value of RB here. You can put the value of RB here. After putting, you will get the value of RA as W by 2. In this way, we have calculated both the support reactions, RA as well as R. So here we have RA, first answer, RA and RB here. We have here RA, RB, both we have calculated. So by using these two, always use summation of moment for any point and summation of force in the y direction 0 to get the value of RA as well as RB. But in examination, in GATE examination, we don't have that much of time. So we are going for the shortcut. So we are going for the shortcut to find the support reaction. And what is the shortcut to find the support reaction? Here, just look at here, shortcut. Shortcuts to find support reaction. Shortcuts to find support reactions. Support reactions. Shortcut to find support reactions here we have. So what is the shortcut here? Suppose here we have symmetrical loading will be here. In case of symmetrical loading here, if we need to find what is RA and if we need to find what is the value of RB, we need to find in case of simply supported beam, in case of point load acting at the center, that means at L by 2 and L by 2, since it is a symmetrical load. In case of symmetrical load, half. In case of symmetrical load, what it can half support reaction. Half support reaction will be there. Half will be in the support reaction. For example, here load acting is W, so half will be W by 2, half will be W by 2. Please remember, do not solve in exam, directly write half. Please remember, half in case of symmetrical loading. In case symmetrical, right? In case of symmetrical loading, half of will be here. Okay. Suppose, for example, here we have one more type of loading. Here we have one more type of suppose beam. Let's say here we have one UDL. Let's say here we have one UDL, and here support reaction RA and RB. Support reaction RA and RB, and UDL will be acting here like say UDL will be W Newton per meter. Then what you will say? You say, sir, first of all, this will be acting like this, na sir. First of all, it will be converted to a point load, which is equal to W into L converted to point load. And here still RA we don't know, and still RB we don't know, still RB we don't know. So half of only, half of WL by 2, and here also WL by 2, half of. So this will be WL by 2, and here also WL by 2. Half of will be here. Half of will be here like this. Okay. Suppose if it is not symmetrical, if point load is not symmetrical, if point load is here like this, if point load is here like this, point load is acting here, which is not at the center, which is not symmetrical, which is at a distance of A from here, which is at a distance of A from here, and at a distance of B from here, B from here, and total distance is L. Total distance is the length L, and here it is like this. Here it is like this only. So how we can get? Very simple. Very simple. How? Cross multiplication. I will write here cross multiply. Cross multiply only. Here we have shortcut cross multiply. In the previous page I have say half of shortcut. Here it is cross multiply shortcut. How it is cross multiply? Just look at here. Here you will say RA na. Here you will say RA. And here you will say RB. Here you will say RB. Very simple. First of all, total load is W. What is the total W? So W divided by total load divided by total length, that is L. Load divided by W divided total length L. And cross multiply. Cross multiply means A will be multiplied to this side and B will be multiplied to, and B will be multiplied to this side. So A will be multiplied to this side here. So A will be multiplied here. A will be multiplied to this side, and B will be multiplied to this side like this only. So here W A by L, and here it is W B by L. So I can write the value of RA as well as I can write the value of RB. So please remember this word cross multiply. Please remember the word cross multiply. So whenever we have this type of symmetrical loading, half of unsymmetrical loading, definitely we can go for the cross multiply. Definitely we can go for the cross multiply. Okay. Now one more shortcut here we have. One more shortcut here we have, and the shortcut is for the point moment acting at a point. And the shortcut is here point moment acting at a point. Suppose here we have a point moment acting here. Suppose here we have at the center point or at any point moment is acting here. Moment is acting here. Suppose here we have, okay, suppose here we have hinge and here we have roller like this only. So what happened? First of all, here I can say it is M by L. Magnitude will be M by L, RA, RB. So here this point A and here is this point B here. Na? So this RA will be, here RA will be equal to M by L, and this side RB will be equal to M by L. Both will be same, which is equal to M by L. But different sign. If one is upward, another will be downward. And how to decide which side upward, which side downward? Suppose it is rotating like this, na? Rotating like this. So what happened? If it is rotating like this, suppose draw the circle. If it is rotating like this here at this point A, at this point A, moment is rotating like this. So opposite of moment will be the support reaction. Opposite of moment here at point A, here opposite of support reaction will be here RA. RA will be equal to M by L like this only. And reverse of RA will be RB. Reverse of RA will be equal to RB. Reverse of RA will be equal to RB. Or you can say like this, here we have, you can say like this, here we have a moment, right, in the clockwise direction. So reverse of this will be equal to RB, and RB will, which is equal to M by L, which is equal to M by L here. So here we have RA M by L, and here we have RB, which is also M by L here. Both magnitude wise equal but opposite in the direction. This is also shortcut. If moment is acting at any point, not a half of L by 2, moment can be acting here, moment can be acting here, moment can be acting here, here. At any point, if moment will be acting, single mode will be acting without any transverse load, then the support reaction will be RA, RB, both will be equal in magnitude, which is equal to M by L, but opposite in direction. How to choose the direction also, I have told you here, how to choose the direction of RA as well as the direction of RB. How to choose direction of RA as well as RB. So I hope you are enjoying this video. Okay. I hope you're enjoying this video. Very good video. Okay, you're enjoying a lot. So in this video, we have covered types of support, types of load, and support reactions, everything. That means we have started shear force as well as bend diagram, and we have done the basics of shear force as well as bending diagram, but we have not done what is shear force, what is bending diagram. So in the next lecture, I will be discussing with you. In the next lecture, I will be discussing with you the shear force and bending diagram, calculation of shear force and calculation of bending moment. I will be discussing it with you in the next lecture. So in this lecture series, as you can see that I am providing you so many videos of almost 25 minute, 30 minute videos. So many videos will be coming, lecture number 1, lecture number 2, lecture number 3, 4, 5, 6, 7, 8, 9, 10, like this only. So please watch all the videos in this series, in this strength of metal series, so that you can get a very good idea of strength of metal. Suppose if you are from the mechanical or you are from the civil engineering, even though no problem, I am telling for both mechanical as well as civil engineering. Mechanical as civil engineering, especially for the gate examination. Okay, and you are watching this video on the YouTube channel of Gate Forum. So like the video, share the video with friends, as well as subscribe this YouTube channel, so that whenever any new video will come, definitely one notification will be provided to you, and definitely you can watch the video at the same time. Okay, so please subscribe this YouTube channel, like video, and as definitely subscribe with your friends also. Okay, thank you all of you for watching the video, and definitely I will come in the next lecture with calculation of shear force and bending moment, and I will teach you how to draw shear force as well as bending moment diagram also. Okay, if you have any query question, please post in the comment box of this video only. I will definitely reply you personally in that comment box only. Okay, bye all of you.